Okay, welcome. I'm now gonna try to show you problems number 19 and number 65. They were both from lesson 4.6. Remember, they were requested and we didn't have time to go through them in class. So I'm gonna try to do this by video. So first of all, number 19 gives you this function and it says, make use of all of your algebra calculus tools in order to find what this function looks like, to basically come up with the graph. All right, so we got to start someplace. So this particular function looks fairly simple in this regard. There certainly is nothing that you could substitute for x that would make this to be undefined or anything like that. So my first observation is that the domain and the range, it looks like there's no restrictions. So we're not going to have any asymptotes or boundaries or something like that. Okay. I mean, something else that's very important, where the zeros of the function. So if you take this thing and set it equal to 0, x to the 5th minus 5x equals 0, you can see pretty quickly that we divide both sides by x. So x has to be equal to plus or minus the 4th root of 1, which is, so in other words, we already know, and by the way, on this graph, the boxes are a little bit too tiny, so I'm going to have each stand for a half. So that's 1, that's 2, okay? So I first of all want to mark, we have a 0 here, and we have a 0, you know, so we've got those going on at plus and minus 1. All right, where what else will equal 0? If you go back, I mean, I didn't show it, but we could have factored this too, right? I could have factored this, and if I took an x out, that's what I probably should have done. Then it would be you know what? I made a mistake on that. Yeah, let me just go back. Let's just let me do the zeros thing again. Sorry about that. But just to be a little bit, I should have factored it right away. So in other words, set it equal to 0. Sorry. So set it equal to 0. And then factor it. And then set each factor equal to 0. And on the other side, you'd have x to the 4th equals 5. And then you'd have to what? Take the 4th root of 5, plus and minus. There we go. Now the 4th root of 5 turns out to be approximately 1.5. So we can see right here, we've got a 0 right here. So we should put that point on the graph. And we should have zeros at about 1.5 and negative 1.5. Again, each line stands for a half, okay? So I already have 3 anchor points on the graph. All right, let's do a little derivative work. What's y prime? 5x to the 4th minus 5. And when is that equal to 0? That's supposed to be minus 5. And 5x to the 4th equals 5. X to the 4th equals 1. And here's what I was thinking before. We have plus or minus the 4th root of 1. So these are critical points. I don't know where they are. You know, all I know is at that point, you remember what a critical point means. The derivative is either undefined or it's equal to 0. So we have either a relative max or a relative min. So if we go back and plug in 1, what do we get? If you plug in a 1, you'll see if you calculate it out, 1 to the 5th is 1. 1 minus 5. So that's going to be negative 4 at 1. So at 1, 1, let's see, each line counts a half. 1, 2, 3, 4. So we've got that point, and we know because it's a critical point, there's a horizontal tangent line there. Likewise, when x is negative 1, you find out it's positive 4. So 1, 2, 3. So there we also have a horizontal tangent. Okay. So we can kind of maybe see what's going on already. Let's just take a look at the second derivative. Pretty easy. It's 20x cubed. And when is that equal to 0? So that'll point of inflection. When is that equal to 0? When x equals 0. So at x equals 0, we have a point of inflection. So it's changing from one concavity to the other. Can you also just look at it real quickly? 20x cubed, when will that be negative? Whenever x is negative, right? So from the interval from negative infinity, I shouldn't have put that second parenthesis on there. So from the interval from negative infinity to 0, we know it's concave down because it's going to be negative. And then when it's positive, so from 0 to positive infinity, then it's going to be concave up. Okay, now we pretty much can see doesn't that pretty much nail it down? I mean, concave down. So this thing has got to be doing something like this. Concave down, point of inflection, starting to change to concave up. And we pretty much have that idea of what this should look like. Now, let me see if I can switch here. We'll try to load a Desmos here. And let's just do a quick check. So what did we have? We had, okay, I got to do this a little differently here. X yeah, I may have to put my keyboard back on. Okay, x to the 5th. What was it? X to the 5th minus 5x. And you'll see we had it staked out pretty good. Do you see how at -1, yep, we had that what did we call it? Critical point at -1,4, and we have another critical point at +1,4. And then there's our point of inflection right at the origin. And you can see we have the function staked out pretty good. So that's a pretty good example of using a number of the algebra and calculus tools at your disposal to try to find out what the function looks like. I know the graph is pretty sloppy, but hopefully you got the idea there. So let's go to number 65 now. 65, this is really a totally different kind of a project here, because here they gave us the graph of the derivative. Do you see that? So this is, I mean, what they're telling you is the graph of f prime. And we have to go backwards and find the graph of f. And then we also have to do f double prime. Now, they give us very many clues. Okay, I mean, all we know, we don't know any points that the graph is on. From looking at the derivative, you cannot gain any actual f points, but we can get f shape. So the first thing I'm interested in is, when is f prime 0? And that would be right here and right here. So in other words, the critical points are at -2 and 2. And because that's when the first derivative is 0. Okay. Also, we know something special is going on here, right? Because when is the first derivative? Well, let me put it this way. What's the slope of f prime at the point I just circled down here on the bottom? 0, right? So in effect, we just found f double prime at 0 is 0. So we just found there's basically a point of inflection at 0. So point inflection at 0. Okay. Also, if you look at the slope of f prime, you can see that at the first critical point, the slope of that first derivative is negative, meaning f double prime is negative. So that means, well, in effect, that means everything to the left of this point down here on the bottom is concave down. So from -infinity to 0, we're on concave down. And if you look to the right, the slope of f prime is forever positive. That means the second derivative is positive, which means past 0, the curve is concave up. Okay, so now what I don't have any points, but already I can see that, you know, I'm just going to make up a point, okay? Because we just don't know how high this graph is. Please note that. So in green, I am going to, I don't know, let's just say, I'm going to just nail down a point. And at that point, we know we're at a critical point, right? At x equals -2, we're at a critical point. And we know the curve is concave down. So this thing has to be doing this type of thing, okay? And I don't know where, but I do know when it hits x equals 0, it's at a point of inflection, so it's starting to do the other thing. And then I know that when it hits 2, we have a critical point again. And all of this, you know, all of this stuff is concave up from 0 on. So I pretty much know that's the shape of the function. I do not know what height it is. So that whole green curve could be shifted up or down. We just don't know. Now, So that's about what we can tell about the original function. So this is the f function. So now using, what should we do? Red. Let's do f double prime. All right. Now, f double prime is the slope of the given original black f prime one. Well, we know right here the slope at this point down in the bottom here, the slope is 0. So at x equals 0, I know that the slope is 0. So I'm going to put a point right there. And I know, do you see how the black curve, it's negative, 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 but it's getting bigger, bigger, bigger. So because this thing is forever concave up, that means it's always increasing. And you can, basically, let me explain. There's basically what f double prime looks like. So how do I know that? Well, here, let me give you another clue. We started off, can you tell that my green f curve appears to be a cubic? Right? It's got 2 turns in it. Remember how a cubic function looks? What's the derivative of a cubic function? A square function. And can you tell that's what the black curve is? That's just a good old quadratic parabola. And what's the derivative of a squared function? A linear one. So that's how that's another clue I use to find out the shape. Excuse me. So, I mean, it's ironic, but f prime, and that one I can nail down as going through the origin because I know the slope of f at this point down here on the bottom is 0. So that's got to be a 0 there. So here's the first time I can nail down a point. But the green curve could be higher, lower, doesn't matter. So that's about, so there's a case where we had to use some different kinds of tools because they started us off in a totally different place, didn't they? They started us off with the first derivative, and we had to kind of go backwards and find the function. And we had to go forwards and find, I mean, actually, f double prime is easier to find than f. You got to really work on your clues to find f. Okay, well, thanks. Hopefully you'll tune in and get something out of this. Thank you. See you in class.